Nobody asked me to look this up. I did it anyway. Number 10. Ancient massive galaxies. Galaxies need cold gas to make stars. Cut the supply and the galaxy dies. Telescopes turned up whole galaxies that shut down star formation shockingly early and faded into red, quiet shells. The James Webb Space Telescope cataloged examples like JADES GZ 701QU, a galaxy that was already dead when the universe was only 700 million years old. Models predicted galaxies would grow slowly. This one burned through its fuel and went silent in what amounts to a blink. 3 mechanisms kill galaxies: supermassive black holes, when actively feeding, blast jets and radiation that heat surrounding gas and blow it out of reach. Rapid starbursts produce fierce winds that eject fuel faster than gravity can hold it. And in dense clusters, galaxies lose gas as they plow through the hot intracluster medium, ram pressure stripping like wind ripping a flag from a pole. Astronomers read dead galaxies the way geologists read rock layers. Star colors and spectral signatures reveal when formation stopped and how fast the decline was. Webb and deep ground-based surveys keep finding these corpses at ages when the universe should still have been building. The implication is practical. If galaxies die early and often, the number of star systems with long, stable eras, the kind needed for complex life to develop, drops. The habitable window is not just about finding the right planet. It is about finding the right planet in a galaxy that stayed alive long enough to matter. Number 9. Gamma-ray bursts. On October 9, 2022, satellites registered the brightest flash ever recorded from deep space. They called it the Boat, the brightest of all time. GRB 221009A came from a collapsing star 2.4 billion light-years away, and it was so intense that it ionized Earth's upper atmosphere from across the observable universe. More energy in 10 seconds than our sun will produce in 10 billion years. One beam, one alignment, no warning. Gamma-ray bursts come from 2 sources. The first is the death of a massive star whose core collapses into a black hole or neutron star, launching jets at nearly the speed of light. The second is the merger of 2 neutron stars spiraling into each other. Both events focus their energy into narrow beams, which is why they can outshine entire galaxies for a few seconds. The danger for a planet is not the visible light. It is the cascade of chemistry the radiation triggers in the upper atmosphere. Ozone breaks apart. Nitrogen oxides form. The shield that blocks ultraviolet light from the surface disappears. Any life below loses its protection. Astronomers now track the afterglows at radio, infrared, optical, X-ray, and gamma-ray wavelengths. Some bursts are a single clean flash. Others arrive as messy storms lasting hours, a behavior that broke the original models and required new engine physics. The probability of a direct hit on Earth is low, but the consequence is extinction, and probability multiplied by consequence is the number that matters. Number 8. Dark energy. 2 teams of astronomers walked into 1998 expecting to measure how fast the universe was slowing down. They used Type 1a supernovae as standard candles, explosions with known brightness that let you calculate distance. The data came back wrong. The distant supernova were dimmer than the models predicted, which meant the space between us and them had stretched more than anyone expected. The universe was not slowing down, it was accelerating. Saul Perlmutter, Adam Rees, and Brian Schmidt shared the 2011 Nobel Prize in Physics for that discovery. They had shown that about 68% of the total energy content of the universe is something that pushes space apart, and nobody knows what it is. Scientists named it dark energy because they had no better word. The cosmic microwave background, the clustering patterns of galaxies, and baryon acoustic oscillations all independently confirmed the same conclusion. This was not one odd result. It was a convergence. Three competing explanations remain. One, a cosmological constant, a fixed energy density woven into empty space, which Einstein once proposed and then abandoned. Two, a dynamic field that evolves over time, sometimes called quintessence. 3. Our equations for gravity are wrong at the largest scales and need revision. Each option leads to a different ending. If the constant holds, the universe drifts toward cold isolation. Galaxies beyond our local group recede past the point where their light can ever reach us. The observable universe shrinks. If the energy grows stronger, space-time itself could tear apart in what is called the Big Rip. If gravity is broken, we rebuild physics from the ground up. How sure are we? Not completely. And that may be the most honest sentence in cosmology. Number 7. Metastable Higgs field and vacuum decay. The Higgs field is the invisible background that gives particles mass. Without it, electrons would not bind to nuclei, atoms would not form, and chemistry would not exist. In 2012, the Large Hadron Collider confirmed the Higgs boson at a mass of 125.1 GeV. The top quark sits at around 173 gigaelectronvolts. Plug both numbers into the standard model equations for the Higgs potential, and the answer lands in the wrong part of the graph. Our universe may not be in its lowest energy state. It may be sitting in a local minimum, a shallow dip on a hillside rather than the deepest valley. The metastable scenario, a quantum fluctuation vanishingly unlikely in any given moment, could nucleate a bubble of true vacuum. That bubble would expand at the speed of light. Inside it, the constants of physics change. Protons and electrons may not bind. Solid matter cannot exist. No warning. No escape. No debris. For decades, this was a thought experiment. The precision of the Higgs and top quark measurements made it a calculation. Most physicists emphasize the probability is extraordinarily low on any human time scale. But the consequence is total, and the math does not care about timelines. The calculation changed how physicists talk about safety. Not the safety of buildings or bridges, but the safety of physics itself. It drove investment in more precise mass measurements at CERN, and opened arguments about whether the metastable window is an artifact of incomplete physics. Perhaps supersymmetry or new particles at higher energies would stabilize the field. We do not know yet. The measurements say we are in the uncertain zone, and the uncertain zone is the one where the question stays open. Number 6. Mysterious cosmic structures. Maps of the sky once looked like random scatter. Then astronomers spotted patterns that should not exist. The Hercules Corona Borealis Great Wall, identified in 2013 through gamma-ray burst clustering, stretches across 10 billion light-years. The cosmological principle, the assumption that the universe is homogeneous and isotropic on the largest scales, sets an upper limit on structure size at about 1.2 billion light-years. The Great Wall exceeds that by a factor of 8. Independent surveys confirmed the problem. Radio telescope mapping, deep galaxy counts, and gamma-ray burst distributions all showed coherent structures larger than the models allow. Giant filaments and voids that are too big, too organized, and too early. Two explanations compete. The first is exotic physics in the infant universe, unknown processes that seeded unusual clumping before the cosmic microwave background formed. The second is observational bias. Subtle selection effects in our surveys that create the illusion of walls where none exist. Neither answer helps. If the structures are real, the cosmological principle needs revision, and with it the age estimates, matter budgets, and growth timelines that depend on it. If they are artifacts, our survey methods have a systematic flaw we have not identified. New instruments and wider maps will settle it, or the anomaly will deepen. Either way, the tidy version of large-scale cosmology already cracked. Number 5. Fast radio bursts. In 2007, Duncan Lorimer and his student David Narkovich were sifting through archival data from the Parkes Radio Telescope in Australia. They spotted a burst of radio energy that lasted 5 milliseconds and came from billions of light years away. One flash carrying as much energy as the sun produces in days, compressed into less time than a finger snap. The signal was real, it was not interference, and nobody could explain it. For years, the Lorimer burst sat alone, and skeptics called it a fluke. Then the Keim Radio Telescope in British Columbia started catching them by the hundreds. Some were one-off events, others repeated. One repeater, FRB 180916, followed a 16-day cycle, active for 4 days, silent for 12, like a clock with no obvious winding mechanism. The leading suspect is a magnetar, a neutron star with a magnetic field a trillion times stronger than Earth's. In April 2020, a magnetar inside our own galaxy, SGR 1935 plus 2154, fired off a radio burst that matched the FRB signature. That was the first direct link between a known object and the phenomenon. But the explanation refused to stay clean. In early 2025, astronomers traced FRB 2024-0209A to an ancient, quiescent elliptical galaxy, a dead stellar population where young magnetars have no business existing. One detection cracked open the question of whether FRBs have multiple origin channels. Then came evidence of binary systems. Plasma from a companion star was contaminating the signal of one repeater, suggesting the source is not isolated. The brightest nearby burst, nicknamed RB Float, arrived from a galaxy only 130 million light-years away and revealed a messy environment of magnetism, dust, and shock waves that no single model covers. The signals keep arriving. The explanations keep fracturing. Number 4. Hostile exoplanets. The first exoplanet atmospheres we managed to read were not friendly. WASP-12. B orbits its star so closely that it completes a year in just over a day. Its atmosphere is being torn away in real time, trailing behind the planet like a comet tail. Kepler 78b is a lava world, a scorched rock orbiting its star in 8.5 hours. TRES-2QB absorbs more than 99% of the light that hits it. Darker than coal, darker than any surface in our solar system. Telescopes measured sodium, potassium, iron, and even titanium oxide escaping from planetary atmospheres. They detected worlds tidally locked so severely that one hemisphere is a molten furnace and the other frozen solid. Hydrogen sulfide and metal clouds showed up in spectra that were supposed to reveal water vapor. Planets orbiting red dwarfs face constant flares that strip atmospheres faster than outgassing can replace them. Each measurement narrowed the habitable list. Rocky does not mean friendly. Close to a star does not mean warm, in a useful way. The search for life did not expand with the number of known exoplanets, it contracted. When you can read an atmosphere instead of just detecting a shadow, most candidates fail. Mission priorities shifted in response. Resources moved toward studying a smaller number of genuinely promising targets in more detail, rather than cataloging thousands of hostile worlds that look good only on a bar chart. Number 3. Rogue planets. Not every planet orbits a star. Gravitational interactions during the chaotic early years of a planetary system can fling bodies outward at escape velocity. Others condense directly from cold molecular clouds and never belonged to a star in the first place. In 2022, the Hubble Space Telescope confirmed the detection of an isolated stellar mass black hole 7 times the mass of the Sun, moving through the Carina Sagittarius arm at about 160,000 kilometers per hour. The technique that detected it is gravitational microlensing, where the invisible object bends and brightens the light of a background star, and it is the same tool astronomers use to detect rogue planets. Surveys now estimate billions of free-floating worlds in the Milky Way alone. Most are frozen and dark, but internal heat from radioactive decay, thick hydrogen-helium atmospheres that trap warmth, or tidal heating from moons could keep subsurface oceans liquid for billions of years, even without a star. The implications cut both ways. A rogue with a buried ocean is a hidden habitat. A rogue massive enough to pass through an established system is a gravitational disruptor, capable of tilting orbits, scattering comets inward, or ejecting smaller planets entirely. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will use microlensing at scale and is expected to reveal the actual population size for the first time. Until then, the number is an estimate and the threat is a probability, but the galaxy is full of things that wander in the dark. Number 2. The Great Attractor. The Milky Way is not drifting. It is being pulled through space at around 600 kilometers per second, or 1.3 million miles per hour, toward a region we cannot directly observe. The destination sits behind the plane of our own galaxy in a band astronomers call the zone of avoidance. Stars, gas, and interstellar dust block optical telescopes completely. The first sign of something wrong came in the late 1970s when redshift surveys revealed that thousands of galaxies were not just expanding away from each other as expected, they were also streaming systematically in the same direction. Something offstage was pulling. Radio and X-ray telescopes eventually pierced the dust. What lay behind the dust was not a single massive object but a gravitational basin, an enormous convergence zone where the flows of around 100,000 galaxies meet. In 2014, a team led by Brent Tully mapped this basin and named it Laniakea, from the Hawaiian for immeasurable heaven. The Great Attractor sits near its center. Our galaxy is one tributary among thousands flowing toward that point. Then the picture got worse. The Great Attractor itself is being pulled toward the Shapley supercluster, an even larger concentration of mass about 600 million light-years beyond. We are not falling toward one well. We are caught in a cascade. Each pull larger and more distant than the last, each one discovered later than the one before. We spent centuries thinking we were stationary, then decades thinking we understood the motion. Now we know the motion has layers we are still mapping. Number 1. The Boötes Void. Robert Kirshner and his colleagues at the University of Michigan were running a routine redshift survey in 1981, mapping galaxy positions in the constellation Boötes. What they expected was more of the same cosmic web. What they got was an enormous patch of almost nothing. The Boötes Void is about 330 million light-years across and nearly spherical. A region of that size should contain around 2,000 galaxies based on the average density of the universe. It contains about 60, and those 60 are not scattered evenly. They trace a thin, tube-like filament running through the center, like the last thread in a torn web. Its center sits about 700 million light-years from Earth. If you were on a planet inside it, the sky would be black in a way no human has experienced. No galaxy clusters visible for tens of millions of light-years in any direction. The isolation is not an artistic impression, it is a measured absence. The leading theory is that the void formed from smaller voids merging over billions of years, the same way soap bubbles coalesce into larger ones. Each merger swept galaxies to the edges and left the interior emptier. But the scale is the problem. Forming a void this large in the available time pushes the models to their limits. The Boötes Void implies that the large-scale structure of the universe is not just building and clustering. It is also emptying, creating deserts. And if one void this large exists at a distance, we can survey. The question is how many more sit beyond the reach of our current instruments. In parts of the cosmos we have not mapped yet. You hear that list and the math shifts. A gamma-ray burst can erase a biosphere. The Higgs field may be temporary. Dark energy is accelerating us toward cold isolation. Invisible planets and unseen gravitational wells move through a universe that is emptying itself at the largest scales. These are not thought experiments. They are measurements, taken with named instruments by identified scientists and published in journals that anyone can check. The response has been practical. Early warning systems for asteroid threats. Space weather monitoring for stellar radiation events. More precise particle measurements at CERN to narrow the vacuum stability question. We moved from treating the universe as a backdrop to recognizing it as an active variable in the survival equation. The shift itself is the real discovery, the one that contains all the others. The universe is dangerous. That is why we keep looking.